class today. All right. Okay. And let me share the notes. Okay, guys, so today we'll begin with section 2.4, and I would like to inform you that next week we'll begin with our lab, okay? All right, okay, for section 2.4, it is all about error analysis and fast convergence. Now, as I told you at the beginning of this course, okay, because our solution is involving an approximate solution and it is not an exact solution, that means the approximate solution compared with the exact solution, they might have a difference, okay? So this difference is called error, all right? Now, what we're gonna do what we're gonna discuss for section 2.4 is we would like to do some analysis based on the error that we have generated from the numerical simulation or from the numerical methods, all right? And then how fast it converge, all right? So in this section, we are going to first investigate the order of convergence first, all right? So there is a long definition for the order of convergence, but I do not expect that you memorize everything, but you have to know the important points, all right? So let us see the definition at the point number 1. So suppose we have a sequence that is denoted by Pn, and this n is started from 0 up to infinity, okay? So we have this sequence Pn that is converged to P. So that means we have this sequence, all right, where the n start from 0 up to infinity that is converged to P, all right? With the condition that Pn not equal to P for all n. So where we know that our Pn is not equal to P for all n, all right? So that means you start from n equal to 0 to infinity, your Pn value will not be equal to the P, all right? Now, if positive constant lambda and alpha exist, so we know that these two constant alpha and lambda, they are positive numbers. So that means our lambda is greater than 0 and our alpha also greater than 0, right? So they are the positive constant, okay? And we have this limit, okay? So the limit for this one you have to remember, okay? So this is the limit when n approach to infinity. So Pn plus 1 is a sequence. P is a convergence, all right? And then the absolute value of this divided by the absolute of Pn minus P power of alpha, which is equal to lambda. So we know that the alpha here is a positive value, lambda here is a positive value, all right? Then we know that the sequence Pn will converge to P of order alpha with asymptotic error constant lambda. So this alpha is known as the order of convergence, and the lambda is known as an asymptotic error constant. Okay, so this is the name for lambda and alpha, all right? So now in the exam, sometimes we'll just let you know, okay, the sequence Pn converge to P of order 1. Then you should know your alpha is equal to 1. Okay, now with asymptotic error constant 0.5, then you know that your lambda is equal to 0.5. Okay, now always remember in the exam, sometimes we do not give you alpha equal to 1. We are not giving you alpha equal to 1 directly, but we write in words. Okay, we'll say that, okay, given a sequence Pn that is converged to 10 of order 1 with asymptotic error constant 0.5. So in this case, you should know that your P is equal to 10, alpha is equal to 1, and your lambda is equal to 0.5. All right? Now, an iterative technique of the form Pn equal to a G is a function of Pn minus 1 is said to be of order alpha if the sequence Pn converges to the solution P equal to Gp of order alpha. Okay, now this one, it sounds like so complicated, right? But don't worry, later on I will show you an example, okay? So what it means that here, Pn, we can write the Pn in a function g with the variable Pn minus 1, okay? So this one is say that to be an order alpha. So this one, if the order alpha is really depend. If the alpha is equal to 1, that means here, this Pn is an order of 1, okay? Now, and if the sequence Pn converge to the P, where here P we can write, either the question will give you P directly, or we can give you the P can be written in a function G where the variable is P, okay, of order alpha, right? So now there are two examples here. So if your alpha equal to 1 and your lambda less than 1, the sequence is linearly convergent. All right. Now, if your alpha is equal to 2, then we say that the sequence is quadratically convergent. So here is really depend on your alpha, whether your alpha is equal to 1, that is linearly convergence, provided that your lambda is less than 1. And if your alpha is equal to 2, then we say that the sequence is quadratically convergent. Okay, now for this course, we only focus on these two, okay? We only focus on these two cases. Other than that, we will not consider because it will be, you're gonna study it in a more advanced course, all right? So now I give you one example here. So suppose we have two scenarios, okay? One, suppose that your Pn is linearly convergent to 0. So you see, linearly convergent. So what that it means? It means that your alpha is equal to 1. Converge to 0. So this is the value that your P equal to 0, okay? With this is the limit. Okay, so this is given in the definition. So you can see from this one. So this is the definition. So now you know that your P is equal to 0. You know that your alpha is equal to 1. Okay. So you substitute into this limit. So this is a given limit. So limit and approach to infinity. So absolute value of Pn plus 1 minus P is divided by Pn minus 1 power alpha. So now we substitute the P. So that means what you're gonna get from this is your limit, okay, and approach to infinity for the absolute Pn plus 1 minus your P is 0, okay, divided by absolute value of Pn minus P. So your P is 0, your alpha is 1, so power of 1. So actually this is equal to the limit and approach to infinity of absolute Pn plus 1 over absolute of Pn. Power of 1, we usually just leave it, okay? So this is the limit that we have obtained, all right? So you see, this is how we get this. All right, and you are given this is 0.5. So what is this value? So this means that your lambda is equal to 0.5. Okay, so these are the information that you have. That is your alpha equal to 1, P equal to 0, and your lambda equal to 0.5. Okay, and that we have another sequence. So remember, this one, if you see carefully, this is a Pn and this is a Pn tilt. Tilt, if you see, there is a curly line or no, there's curly thing on top of the Pn. So we know that our Pn is not necessarily equal to your Pn tilt. Okay, so I call it as a Pn tilt. Okay, so we assume that they are different. All right, so this sequence is quadratically convergent to 0. So quadratic, you know that your alpha equal to 2. And converge to 0, this value represent your P equal to 0. All right, so you can call it as a P tilt, okay, to differentiate the P and the P tilt, okay? With the same asymptotic error constant. So this one referring to your lambda. So this value represent lambda equal to 0.5. Okay, so you do the same thing. How to get this? So we know that this is actually from the limit and approach to infinity from the formula. So you have Pn tilt n plus 1 minus P tilt. Okay, divided by Pn tilde minus P tilde power of alpha. Next, we substitute the P tilde. Okay, so this one we have Pn plus 1 tilde minus P tilde, that is 0, divided by Pn tilde minus 0, power of alpha, so the alpha is square. So from here, we can simplify. This is equivalent to the limit of Pn plus 1 tilde over absolute value of Pn tilde square. Okay, so this is how we get this. Okay, and 0.5 is the lambda value. Okay, so what we're gonna do is, for simplicity, we assume that for each n we have, okay, how you get this, all right? So guys, do you mind that I write it on another piece of paper, because I need a larger space, okay, so that I can show you better. Okay, so let me stop sharing this page and I will share with you on another page. Okay. Okay. Okay, so let me write down the information that we have discussed just now. So the first information there is for the linearly convergence. Okay, so the linearly convergence, the first thing that we have will be the absolute value of, oh, sorry, I should write down the limit. Okay, so the first information is we have the limit and approach to infinity, the absolute value of Pn plus 1 over absolute value of Pn. This is equal to 0.5. Okay? The second information that is referring to the quadratically convergence, so we have the limit and approach to infinity for Pn plus 1 tilde over Pn tilde square. This is equivalent to 0.5. Okay, now for simplicity, okay, for the case of simplicity, what we're gonna do is we do not consider the limit first, okay? So we consider there are two. So first, there is your Pn plus 1 divided by your Pn, that is equal to 0.5, okay? So from here, what we're gonna obtain will be, I move this Pn to this side, so that means I have my Pn plus 1 is equal to 0.5 Pn. Okay, so next, I want to know what is my Pn. So Pn here is equivalent to our 0.5. So you see, when you have n plus 1, here is n. So if I have n here, that means here is Pn minus 1. Okay, so these are the information that you can derive from this info. Okay, so you see Pn plus 1 equal to 0.5 Pn. So what is a Pn? So the Pn here, because you have n plus 1 minus 1, so here you should have n minus 1. Okay, so you get this information. All right, so let me put it in the red box. This is how we generate. Okay, second information, so this is the first one, okay? Second information that we have, that will be Pn plus 1 tilde, okay, divided by Pn tilde, okay, square, that is equivalent to 0.5, okay? So from here, we will have absolute value of Pn plus 1 tilde. This is equivalent to 0.5 Pn tilde square. Okay, so what you're gonna do if I have Pn tilde? So that means this is n plus 1 minus 1. I get n, right? So you see, n plus 1, and next we minus 1, okay? This is how we obtain this is equal to n. So for the n case, so we have a n minus 1. Okay, we have to do for both sides. So that means this is always equal to n minus 1. So this is how we get Pn tilde that is equal to 0.5. This is our Pn minus 1 tilde squared. Okay? Now, I put this in a box so that for you to differentiate what we have derived. All right? So next, what we're gonna do is now for the linear convergence scheme. Okay, for the linearly convergent scheme, that means we are going to look at this case. Okay, so this is a linearly convergent scheme. Okay, so this one is referring to, okay, let me erase this part because I need to write something here. Okay, so here this is referring to the quadratic, okay, quadratically convergent scheme. Okay, so one is linear, one is quadratic. Okay, so now let us focus one by one. Okay, so first of all, let us look at the linear convergence scheme. Okay, so let us take a look for the linearly convergent scheme. Okay, so we have, okay, what do we have? We have from the limit, okay, we know that our Pn minus P over Pn minus P, that is equivalent to your Pn minus 0, okay? This is equivalent to Pn, okay? How you get this Pn minus P? This is from the definition. You have the Pn minus P. This is the convergence, okay? So what is your Pn? So the linearly convergent scheme that we have for Pn is equivalent to this one. Okay, this is our Pn, all right? So Pn is equivalent to, this Pn is equivalent to 0.5 Pn minus 1, okay? After Pn minus 1, how you gonna find? We want to find, you start from n, right? I want to find what is, how I'm gonna write this Pn in terms of P0. Why P0? Because usually P0 is given in the question because that's the initial value. Okay, you see, whatever numerical methods, you usually will be given an initial value or ask you to have guess what is your initial value. So that means we always have the information of the initial value. Okay, so in this case, Pn, we do not have the information. So what you're gonna do, we need to base on the P0 to get the information of Pn. Okay, Pn can be arbitrary number, all right? So what you're gonna do is we try to write in terms of P0, okay? Now, the next one, after Pn minus 1 is Pn minus 2, right? So at the end, you should know, you should have something in terms of P0. So this is what we want, actually, absolute value. I'm sorry, this one should be absolute value, okay? You want to find some things that you can write in terms of P0. Okay, so how you're gonna do? You should do the minus minus until you get the 0. All right. So what you're gonna do is next we try. Okay, Pn minus 1. The next one will be Pn minus 2. Okay, how to get the Pn minus 2? So we want to find what is our Pn minus 2. So we know that 0.5. Okay, Pn minus 1. How to get a Pn minus 1? So based on this, okay, it's actually based on this one. Okay, so you see, next I want to find Pn minus 1, correct or not? Because this is n plus 1, start from n plus 1. Next we have Pn. Next I want to find what is my Pn minus 1. So how you can get the Pn minus 1? So you see n So this is n minus 1. So this is equivalent to 0.5 times with 0. Sorry, this is 0. I'm sorry, I should times. Okay. The next one will be Pn minus 2. You see, Pn plus 1. So how to get the Pn? Here we do minus 1, we get this. Okay, then here we minus 1, we get this. All right, so how to get the Pn minus 1? So that means we do minus 1, we get this. Okay, how to get n minus 2? We minus 1 from this and we get this. Okay, so next, if you want to get Pn minus 2, how are you going to write? This is equivalent to 0.5 Pn minus 3. Okay, so this is how we get it from here. So what you're going to do, we need the information of Pn minus 1. So you substitute this information. So we know that Pn minus 1 is equal to 0.5 times absolute value of Pn minus 2. So you substitute this one. Okay, you substitute this one into the formula down here. Okay, so now I know that I'm gonna substitute my Pn minus 1. This is equivalent to 0.5 Pn minus 2. Okay, how we get this? Okay, let me minimize a little bit just to show you. So we actually substitute this one, okay, the one that I have highlighted, okay, Pn minus 1, this information, okay, you substitute into here. Okay, that is equivalent to this term. Okay, so this Pn minus 1, we substitute, that is equal to 0.5 Pn minus 2. Okay, so next, I hope that you are clear. Next, we do Pn minus 2. So how, okay, you simplify first. So 0.5 times 0.5, so that means I have 0.5 squared times Pn minus 2. Okay, so next, how to get the Pn minus 2? It is from here. You substitute Pn minus 2 equal to 0.5 Pn minus 3 into this term. Okay, into this term. So we will get this is equivalent to 0.5 squared times 0.5 Pn minus 3. Okay, so let me maximize. Okay, and let me erase this one. Okay, so that I can have some space to write. Okay, so now I simplified this one. So I have 0.5 cubed and then Pn minus 3. Okay, now I would like to draw your attention what you have seen. Okay, you can do some analysis. Okay, so first, let us take a look for this part. Okay, now I would like to draw your attention. You see, if I have n minus 1, what is the power here? You see, this is actually 0.5 power of 1. Agree with me? So you see, I just highlight for you for you to analyze. This is 1. So you see, when you have n minus 2, you see your 0.5 here is power of 2. When you have n minus 3, your 0.5 here is power of 3. Okay, now I want to ask you, okay, let's say, okay, you do something, you do then suddenly I have 0.5 power of, I want you to fill in, this is Pn minus, let's say minus 8. What do you have here? 0.5 will be power of 8. Yes, thank you, Daniel. So you see, so this is matching, right? So now I want you to do. And at the end, I want to know what is my 0.5. And then here, I want to have T0. What how you gonna get 0 here? What do you think? How you get a 0? N minus what equal to 0? N minus n, correct or not? Because n minus n, you get 0, correct? So what do you expect? The 0.5 will be power of n. Get it? You see, if you have n minus a, here will be 0.5 power of a. If you have 0, how you get a 0? Because of Pn, n minus n. So you want to have n minus n, here it should be 0.5 power of n. Okay, is it clear right now? So what can you make a conclusion? So I make a summary. So summary will be, sorry. Okay, so summary will be, okay, I have from Pn minus P, which is equivalent to Pn, okay, actually it's minus 0, I just write, that is equivalent to your Pn. Next, you have it is your Pn that is equivalent to 0.5 Pn minus 1. And next, we know that you have 0.5 squared, that is your Pn minus 2. Okay? And next, what you have will be, if I have n minus 3, so I have 0.5 cube Pn minus 3. And you do dot, 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 at the end, you have, this is equivalent to 0.5 power of n, this is P0. Okay, so this is the information that I want you to draw the attention, how you get to P0. You see, you always have the information of P0. Okay, when you have the information of P0, you will find what is your Pn minus P sequence converging to which value. Okay, now this is for the linear. Okay, now for the quadratic, we do the same thing. That means we start from n, and then you want to do until until P0. Okay, P tilde 0. Okay, so how you gonna do it? Okay, now, so let me write it down a little bit to prompt you. So the next one is we want to see is a quadratically, okay, convergent scheme. Okay, so how we get this one? So always remember we have the Pn tilde minus the sequence. This is a sequence of Pn tilde minus the convergent points. There is a P tilde. So this is equivalent to, given in the question, it is the sequence Pn tilde converge to 0. So you converge to 0. So that means your P tilde is 0. Okay, you simplify this, you get this is actually Pn. If it is convergent to 1, that means we have a Pn tilde minus 1. If it is converging to 0.8, then we have a Pn tilde minus 0.8. Okay, but this case, it is converged to 0. Okay, for the convergence, for the quadratically convergence, so we need to refer back to the Pn tilde thing. So this is a quadratic convergence scheme. So this is the one that we would like to refer. So Pn tilde is given, this is equivalent to 0.5 Pn minus 1 tilde squared. Okay? So next, I would like to ask you, what is the equation for Pn minus 1 tilde? What do you get here? It will become 0.5. Yes. Next.
Pn minus 2.
Yes, very good, Daniel. So do we need a square?
Square.
Yes, exactly. Okay, you need a square for this one only? Or you need to square everything again? Or do you think, am I right, the right answer?
I think this is the right one.
Yes, you're right. Okay, very good, Daniel. You can sit for the exam right now. Good job. Okay, yes, this is the correct one. So Can you see? This is how we get it. So what you're gonna do, you have to substitute. Okay, I highlight this term. You have to substitute your Pn minus 1 till this term into the equation that we have discussed just now. All right, so I put it in the quadratic convergence scheme here. So I'm gonna substitute this Pn minus 1 till equal to 0.5 Pn minus 2 till square. Okay, don't forget the square here. So I'm going to substitute your Pn first. I substitute Pn first. So Pn, that is Pn is equal to 0.5 Pn minus 1. Sorry, Pn2, that is equivalent to 0.5 Pn minus 1 cube square. Next, I'm gonna to substitute this term using this one. Okay, so now let me write my Pn2. Okay, let me minimize. Is it able for me to show you the Pn2? I think it's too small, okay? So I'm sorry. So I cannot squeeze for you, but you just remember. So your Pn tilde is equal to 0.5 Pn minus 1 tilde square. So I'm gonna substitute here. So this one, I get it. This is 0.5 Pn minus 1 tilde square. So next, I'm gonna substitute this Pn minus 1 tilde, which is equivalent to this one. All right, I'm gonna substitute this one into the formula. So I will have, this is equal to 0.5 times. Remember, there is a square out here, so I need to put something square. Okay, Pn minus 1, this is equivalent to 0.5 Pn minus 2 tilde square. Yang ini you kena hati-hati ya. Jangan lupa square ni. Jangan lupa you ada square kat sini. Kalau ada square kat sini, you mesti letak square kat sini. Alright? Kalau you lupa, saya pun lupa bagi markah. Okay, that's a concept. Alright. Okay, so what you're gonna do, we simplify this one first. So you actually get, I want to get the square. So I have 0.5 times, actually this is 0.5 square times Pn minus 2 tilde. I have square and then I square again, so I will get power 4. Okay, so after that, I simplify again. So 0.5 times 0.5 square, I have 0.5 power of 3 and times with Pn minus 2 tilde power of 4. Okay, next, how to get the Pn minus 2 tilde? Okay, get back to your given question. Okay, so here I have Pn minus 1, right? Tilde. How I'm gonna get my Pn, I use the blue. How I'm gonna get my Pn minus 2 tilde? Can someone tell me? This is equivalent to 0.5 Pn minus 3 tilde square. Okay, so what you're gonna do, I'm going to substitute this Pn minus 2 tilde, which is equal to 0.5 Pn minus 3 tilde square. I'm gonna to substitute this term into here. Okay, I'm gonna substitute this one. So what I'm going to have will be, this is equivalent to 0.3 times something power of 4. So what is your Pn minus 2 tilde? So your Pn minus 2 tilde, that is equivalent to 0.3 Pn minus 3. Let me write properly. Okay, I'm sorry. Okay, so I will have, this is Pn minus 3 tilde square. Okay, so now we begin to simplify. The quadratic is a little bit convergent, but it's not super hard. So I will have 0.5 power of 3. Okay, 0.5 power of 4. So I have a 0.5 power of 4 here. So here I have a Pn minus 3 tilde square. And then power of 4. So in a total, I will get Pn minus 3 till power of 8. How to get 8? 2 times 4. So we get 8. So I simplify this one. So 0.3 square and then times 0.5 power of 4. So in the total, I will have 0.5 power of 7. How to get a 7? 3 plus 4 give us 7. Okay. And next, times with Pn minus 3 till power of 8. Okay. And next, you do it again. Okay. And then you repeat. Okay. But you can see some pattern. Okay. So what is a pattern? So let me move up a bit. Okay. So you see, first of all, I write here power of 1. Okay. So this is 0.5 power of 1. Okay. Let me do some highlight. Okay. So you see, when I have n, this is power 0.5 power of 1. Okay. And next I have Pn minus 1. Okay. And I have a square here. Okay. If I have 3, I have power of 4. Okay. And 1 here. Okay. 1. And this is 2. Pn minus 2. Okay. You see, I know that. Okay. 1 here, I get 2. 2 here, I get 4. Okay, 1 here, and then 2 here. 2, Pn minus 2, 0.5 here, I get cube. But here is power 4. Okay, maybe you still cannot see the pattern. So what about this one? Can you see the pattern? When here is 3, I have 8. And then here I have 7. Okay, from here, I know one thing. Okay, I know that if I have a 2 out of 3, I have 8. Correct? If I have 2 out of 3, in order for me to get 7, I know that minus 1, I will have 8 minus 1. Sorry, I'm too eager to write the answer actually. So it's actually minus 1 first. Okay. So minus 1 and I get 7. So this is perfect match. Okay, what about this? Okay, I put a box here. If I do the same thing here, can I get the answer? So you see, if I have 2 power of, how I get a 3? Because the one that I had like n minus 3, right? So if I have 2 square, 2 power of 2, so I get this is 4. Okay, so now how am I gonna get a 3? So I know that I have 2 square minus 1. So this is equivalent to 4 minus 1. I get this is 3. This is good. It's match. Okay, the concept is matching. Okay, what about 1? So here, if I do, I know that 2 power of 1, I get 2. Okay, next, I know that in order for me to get a 1 here, so you see 1 here, so I know that 2 power of 1 minus 1, I get, this is 2 minus 1, and I get 1. Oh, you see, you can apply this concept, right? So we start from 2 power of 1 equal to 2, and then 2 power 1 minus 1, I get 1. Next, because this is n minus 2, so now I have 2 square equal to 4. And then 2 square minus 1, I get 3, so it's satisfied. Next, I do this. 2 power of 3, okay, equal to 8, and then 2 power of 3 minus 1, I get 7. Okay, now, you feel like this is correct, but you want to make sure it is really correct. How? Okay, next, we want to substitute Pn minus 3 till. Okay, how to get a Pn minus 3 till? Okay, come back here. Okay, so how I'm gonna to get my Pn minus 3 till? So this is actually equivalent to 0.5 Pn minus 4 till square. So you substitute this Pn minus 3 till equal to 0.5 Pn minus 4 till square into here. Okay, into here. So now I will have, this is equivalent to 0.5 power of 7. I have something here, power of 8. So what is my Pn minus 3 till? It is equivalent to 0.5 Pn minus 4 till square. Okay, you simplify this. Okay, I have actually 0.5 power of 7 times 0.5 power of 8, and then times Pn minus 4 till 2 times 8 is 16. So summarize this, or you have 0.57 plus 8, you have 15, okay, times Pn minus 4 till power of 16. Okay, now you apply this concept. Next, we're supposed to get 2 power of 4. What is that? And then 2 power of 4 minus 1. So can we get 2 power of 4 is equal to 16? And this is 16 minus 1, which is equivalent to 15. So you see, it match, right? So you see, it match with the concept that we have. That is, you see, 4, I get 16. So I get this 16. And 2 power of 4 minus 1, okay, I get 15. So I get this. So at the end, what you're gonna do? Dot, until the last one, we want to write P tilde 0. So that means I want to know what is my 0.5 power of, and then times P0 tilde, and what is the power. So I want to know what I'm gonna fill in for the power here. Okay, so I know that in order for me to get 0, how you gonna get the 0? This one, I know that my Pn should be n minus n, correct? N minus n give a 0. So that means here, I'm gonna write this is 2 in a box. This is 2 power of something. Okay, what is a something here? Equal to something. And next, I have the 2 power of something minus 1 equal to something here. So how you gonna get? At first, I know that this is 2 power of n. Okay, and next, here I have 2 power of n minus 1. Okay, so I just write this is actually 2 power of n, and this is 2 power of n minus 1. So you're gonna fill in here. So let me put a larger box. So I know that this is 2 power of n, and I know that this is a 2 power of n minus 1. Okay, so let me write. Okay, let me write properly. Okay, let me erase this one. I want to write properly. Okay. So at the end, I know that I'm going to have, this is 0. I want a black color. So this is, okay, this is 0.5 power of 2 power of n minus 1. And time with T0 tilde, okay, power of 2 power of n. So this is what I get. Is it clear, guys? So at the end, we have this formula. So I draw this using a red line. Okay, so now what you're gonna do is, okay, let's say we want to know what is the speed of the convergence. Okay, for simplicity, I just want to show you nicely. I want to show how it converges. So let's say, let us assume, okay, so maybe I write it down, summary. So for the linear convergence, we have 0.5, let me write properly, okay? So I have a 0.5 power of n times P0, okay? For the quadratic convergence, we have final answer, okay, yeah, let me write it properly. I should write this is Pn, okay? I should not leave the answer for the Pn. So I have my Pn, okay, can be approximated by 0.5 n and then P0. For the quadratic, I have the Pn tilde that is approximately by 0.5 2 power of n minus 1 times P tilde 0. and then this is 2 power of n. Okay, this is a summary, the final answer, the one that I draw the red line. So that's the final answer. Okay, now, so what I'm gonna assume is, let us assume the initial value P0 equal to your P tilde 0 equal to 1. So you see, this is the initial value. Okay, usually initial value is either given or you have to guess or you choose. All right, so let us assume our initial value for P and P tilde is equal to 1. So what you're gonna do, you substitute into the linear convergence. So that means now I'm going to have my Pn. Okay, I think I better write here. Okay, so I'm going to have Pn is approximately by 0.5 power of n, and then P0. Now I get this is equivalent to 0.5 power of n times 1. So times 1, I'm not going to write. Okay, so this is your Pn. Next, for the quadratic, I have the absolute for Pn tilde, that is approximately by 0.52 power of n minus 1 times P0 tilde. This is 2 power of n. So I substitute 1. So actually I have this is 0.52 power of n minus 1 times 1 power of 2n. 1 power of anything, you get 1. Okay, so that means I have this is equivalent to 0.5 2 power of n minus 1. So I put it in the box, right? So this is the quadratic part. Okay, so next, you can draw a table. Okay, so you draw a table that is really easy. Okay, draw a table. And again, as I told you, okay, put an n here. And then here is a linearly convergent scheme. I'm sorry, I just write in short, okay? So we have the sequence Pn from n equal to 0 up to infinity, that is approximately by 0.5 power of n and P0. Okay, this is the case. So the P0, I do not want to write, so this is equivalent to 0.5 power of n. Okay, it's from here, right? From here. And for the quadratic convergence scheme, so we have the sequence of Pn tilde, okay? And from n equal to 0 up to infinity, this is approximately by 0.5 power of 2n minus 1. Okay? Okay, this is the one that I mentioned. This is here. Okay, it's for here. Okay? So now you begin. If your n is equal to 1, okay? Okay, if you want to, you ask me, can I start from 0? Yeah, no, because n0 you already given, okay? That's the initial guess. So we start from P1, okay? P1, what is the answer? So we have 0.5 power of 1, you get 0.5. Now this one you have 0.5 power of 2 power of 1, so you get 2. 2 minus 1, that is 1. So you have 0.5 power 1, you get 0.5. Okay? Next, when n equal to 2, so you have 0.5 squared. So you actually get this is 0.25 if you use your calculator. So what about this? Okay, n equal to 2, so your 2 power of n minus 1 is equal to 2 squared minus 1, this is equal to 3. So now you have 0.5 cubed. So your answer is 0.125. Okay? And you continue to do. Okay? So you continue to do. So let me stop sharing. I think it is stated in your notes. So let me share your notes. Okay, here we go. Okay, so I don't want to I don't want to repeat the calculation. So this is from your table. So you see, This is the one that we generate. Okay, I only do up to 7. If you want to proceed, you can proceed. But I want to tell you the summary, okay? So if you see from this table, when n equal to 1, it is okay, same value. Okay? Now, when n equal to 2, if you compare this value and this value, which one is larger? This one is large. And this one is small, larger. And this is smaller. Correct? So you want it to converge to the 0, right? Because you still remember your P n sequence converge to your P, and your P value is equal to 0. So for this one, the sequence P n tilde, okay, converge to P tilde. So what is a P tilde value? It is 0. So now you want to see which one converge to 0 faster. Okay, so we compare when n equal to 3, you see this is 1.25. So this is always larger, but this value is smaller. Okay, and this value is equivalent to this value, right? Okay, when you come to the n equal to 4, oh, this is 0.0625. But this one is already 0.000 1, 2, 3, 4, 3, 0, 5, 1, 8. You see, which one converges to 0 faster? Of course. If you see, when you calculate n equal to 7, you see this one is almost 0. Okay, this one still a bit far from 0. So of course, who is the winner? This is the winner. So the quadratic convergence sequence will show you the convergence to 0 much more faster than the linear convergence sequence. So in this case, quadratic convergence sequence is much more better because it converges faster. Okay, so here I explain. You see, the quadratically convergent sequence is within 10 power negative 39 of 0 by 7 term. Okay, at least 126 terms are needed to ensure this accuracy for the linearly convergence sequence. So this one you can rewrite as a 0.58775 times 10 power negative 38. Okay, so that's why how you get this 10 power 38. Okay, so you see, so in this case, quadratic convergence sequence converge much more faster compared to the linear convergence scheme, convergence sequence. Now, in order for the linear convergence sequence to converge to 10 power of negative 38, you need to do up to n equal to, your n should be greater than or equal to 126. So I'm not sure you want to do n greater than 126. I don't think you want to do that, right? So in this case, the quadratic convergence is the winner, okay? Now, but this does not happen all the time, but you just depend on what is the value of your convergence, all right? So you need to create a table in order for you to make a conclusion, all right? So this is the meaning of the order of convergence and the fast convergence thing that we have discussed. All right. Okay, guys, do you have any question about the order of convergence, this section 2.4, the order of convergence and the fast convergence thing? No? Okay, if you have no other question, so I would like to proceed for the next section. That is the properties of bisection method. Okay, now remember, so far what we have learned. Okay, so let me write here. So far, you have learned in this chapter, so you have a bisection method, and you learn about Newton, and you learn about secant. Okay, and then next you learn about the order of convergence, and yeah, I just put order of convergence. Okay, order of convergence. Okay, so what we're gonna do next in the next section is we want to see what is the properties of the bisection. Okay, so they are good and bad thing of bisection method. Okay, the good thing of bisection method is it guarantee to converge. Guarantee. The words of guarantee is so powerful. Next, the error bound is guaranteed to decrease by half with each iteration. Now, can you tell me why it is decreased by half? Why not by 1/3? Why not by 1/6? Why not by 1/10? But why it is 1/2? Can someone tell me what is the reason? No? Okay, because remember, bisection method, you need to find the midpoint. Am I right? So the midpoint is A plus B divided by 2. So that's why it is decreased by half, because every time you take the interval, you're going to chop the interval into half. Okay, into the half, and then after that, you analyze the half of the half interval. So you have interval A, B, and then you know that this is your x1, right? So your x1 is equal to A plus B over 2. So this is the midpoint, okay? So after that, let's say we are going to consider in between A and x1. Then next, you need to find the midpoint. So this is your x2. After that, let us consider again in between A and x2, you need to chop into half again. So this is x3. Then after that, if you want to consider for another half, let's say it's A and the x3, you chop into half again. So every time you chop into half and half and half, and you only focus the one that you chop. Okay? So the half that you have considered. So that's why it is decreased by half with each iteration. All right? Now, the disadvantage, the bad thing about bisection method is it converge slower, okay, slower than other method. Most of the numerical methods. If you compare bisection method with Newton's method, or you compare bisection method with the secant method, most of the time, bisection method converge slower. Okay, so this is a disadvantage. The good thing is it guaranteed to converge, and the error bound is decreased by half with each iteration. All right. Okay. After this, we are going to look at the properties in between Newton's method and secant method. Okay, because we look at the bisection method. Next, we want to compare Newton's and secant. Why? Because secant method applies. They use a gradient from the Newton's method, right? So we want to compare. So since these two are related, what are the difference between these two? They also use the concept of gradient. Find the tangent line. Do you remember that? Find 2 points, right? But what are the difference between these two methods? Okay, first, Newton's method converge more rapidly compared to the secant method. So that means Newton's method converge faster, okay? Converge faster than the secant method. So this is a good thing of the Newton's method. Next, Newton's method requires 2 function evaluation per iteration. So you need to have the information of the fxn and f prime xn. But for the secant method, you only need one evaluation. Okay, that is your fxn at the current iteration, and you use the information of a fxn that you have calculated before. Okay, so that means secant method required less computation time compared to Newton's method for each iteration. Okay, so this is the thing, because you have to look at the formula for the Newton's method. Okay, so for the Newton's method, the formula is xn plus 1 equal to your xn minus fxn. Please correct me if I written the formula wrongly. Okay, but for the secant method, I can't remember. Let me find. I think the secant is involved xn plus 2 equal to xn plus 1 minus something. Let me find it back. Okay, let me double check. Where is my Newton's formula? Just to make sure I written it correctly. Okay, so the Newton's method is correct. What about the secant? I can't remember. Okay. Oh, okay, I found it. So this is minus, this is xn plus 1 minus xn times fxn plus 1. And then over, this is your fxn plus 1 minus your fxn. Okay, so you see, xn and xn plus 1, you actually get it before that. Okay, so that's why you only need to calculate one new value. So that is your fxn plus 1. You need to calculate, okay? Because initial value is given, so you can get it. All right. So you see, initial value is given. So when n equal to 0, this info, this info, this info, and this info, you have it. But the next one, so when n equal to 1, okay, you want to calculate for the next n, you need to find what is your fxn plus 2. Okay, so here you need fx0 and fx1. Usually this one is the initial value. When n equal to 1, so that means this is equal to fx2. So this one you do not have it, but you need to calculate by yourself. So this is the meaning. Okay, so you only calculate one evaluation for each iteration. But for the Newton's method, you need to do two. Okay, so this is the meaning. Now, the third point, both methods try to approximate a problem by another problem that can be solved more easily. That is, you solve a linear equation yx equal to 0 to approximate a solution for a non-linear function fx equal to 0. So this is known as a linearization. What it means, you have a problem, okay? You want to find the root. But how you're going to find the root? You use a tangent line, okay? You use a tangent line. So this is a tangent line. We know that tangent line is equivalent to the linear line, okay? Or linear equation. Okay, so this process is called linearization. Okay, both using, you want to find what is the root for this function fx, okay? But you do not find it directly using the function fx, but you are looking for the tangent line first. From the tangent line, you approximate the solution. So this is called linearization. Okay, so the next one, okay, I think I'm done with this notes. Okay, yes, we are done for the section 2.3. So we are going to the section 2.5. Okay, now, before we continue for the section 2.5, which is a little bit longer, the method is a little bit longer compared to Newton's method, Seeker method, and bisection method. Okay, so you need to put a little bit more attention, I guess. All right, so let me share the notes. Okay, guys, today I will not give you the 5 minutes break, okay, because I'm afraid that I may not be able to complete this section during today's class. But I wish to complete this section, this Mueller's method within this class, okay? If we end earlier, then you can rest earlier, all right? So I'm sorry for that. So you need to bear with me a bit, okay? Now, section 2.5 is about Mueller's method. Okay, now, Mueller's method is a generalization of Seeker method. So that means, you see, Newton, Seeker method. So Seeker method apply the similar concept of the Newton's method. For the Mueller's method, it is using the general form of a Seeker method. So they are actually all related to each other. All right, but what are the differences? Okay, so before we introduce you how the implementation of Mueller's method, okay, let me draw your attention, okay? Now, I would like to let you know, sometimes when you study different textbooks, they may use a different notation, but actually they represent the same meaning. Okay, these are the common representation, okay? Now, some of the textbook, they will use P0, some of the textbook they use x0, so they are actually the same thing. Some of the textbook they use p to represent the point, okay? Some of the textbook they use xy to represent the point, okay? So here I would like to let you know, in our case here, some of the textbook that you have seen, if they use p0, actually they're referring to the x0, okay? P1 referring to the x1 and the P2 referring to the x2, okay? Now, next, I would like to show you what are the difference between secant and Mueller's method. Even though they use even though Mueller's is applying the generalization of the secant method, but they must have a difference. All right, but what are the differences? Okay, first of all, let us see at the implementation. Okay, secant method we need two initial conditions. Okay, or two initial points, all right? In order for us to calculate the next approximation, that is your xn plus 2, okay? So this is your xn plus 2, that is to find the root, okay? Now, for the Newton's method, one initial condition is needed, and we need two initial conditions, but do you remember, for the Newton's method, we need two initial conditions, okay, or two initial points. One is x0 and then fx0. But another one is x1 with fx1, right? But our fx1 is 0. So this is the Newton's method, okay? For the secant method, you have x0, fx0, and you have x1, fx1, and your fx1 not necessarily 0. Okay, so this is the difference. Okay, now for the Mueller's method, you need three initial points. So one is x0, fx0, second is x1, fx1, and the third one is x2, fx2. In order for you to find the next approximation, that is for your x30. This is so-called the expected root. Okay, now if the stopping criteria is satisfied, then you stop. If the stopping criteria is not satisfied, then you proceed. Okay, so this is the concept. This is the implementation. Now, for the concept will be Newton's method, secant method, you use straight line. Okay, you use straight line or the linear equation. Okay, so all this is called linear equation. That is y equal to mx plus c. So the m here is a slope or the gradient. Okay, to approximate the root for a nonlinear curve x. Okay, however, for the Mueller's method, you use a quadratic curve. That is your y equal to ax squared plus bx plus c to approximate the root for a linear curve. All right, so these are the difference. So I repeat, for the Newton and secant method, we use straight line, that is a linear equation, to approximate the root for a non-linear curve. Okay, for the Mueller, we use quadratic, okay, to approximate the root for a non-linear curve. Okay, so the quadratic is in the form of y equal to ax squared plus bx plus c. All right, okay, so next, the algorithm. Okay, here, okay, we know that Mueller's method using the concept of a quadratic polynomial. So we start with fx equal to ax squared plus bx plus c, okay? But here the x is you need to minus with the point 2, p2, and the x here minus with p2, okay? So we expect that this quadratic polynomial passes through these 3 points. Okay, so what we're gonna do for the next is we want to know what is our A, what is our B, what is our C. Okay, there is no value. We don't know what is our A, B, and C. So what you're gonna do, we need to find. How to find? Based on 3 information that we have. There is an initial point. So we have 3 initial points. You see, we have 3 unknowns. Okay, so we have 3 unknowns, that is A, B, and C. So what we know, we have 3 points. So we have P0, F, P0. We have P1, F, P1. And we have the third point, that is your P2, F, P2. So these 3 are our initial points. Okay, so you see, You need to find 3 unknowns. So we have 3 initial points that can help us to find the 3 unknowns A, B, and C. Okay, how you gonna do? Substitute first your point in the first initial point into the equation. So let's say we have a point, how we get this. Okay, so let me stop sharing this. I need a paper. Okay, let me write on this piece of paper. Okay, so what? Okay, we have fx equal to a times x minus p2 squared plus b times x minus p2 and then plus c. Okay, so we have the initial point. Okay, so one is x0 f. Okay, if you want to use p, we use p. Okay, I think I realized that our notes we use p, not x, so I just follow our notes. And next we have our p1 at p1. And next we have our p2 at p2. Okay, so first we use first initial point. Okay, so what do we get? Okay, so we substitute x equal to p0. So we have x is p0 equal to a times x, that is p0 minus p2 square plus b p0x, this is our x. Okay, and minus p2 plus c. Okay, next we use p1 fp1. So what do we get? So we get fp1 equal to a times p1 minus p2 plus b times p1 minus p2 plus c. So we have a times p1 minus p2 squared plus b times p1 minus p2 plus c. Okay, next we use the third initial point. Okay, so this is equal to p2 f p2. So what do we get? Okay, substitute into the formula where the x is p2. So fp2 is equal to a times p2 minus p2 squared plus b times p2 minus p2 plus c. So p2 minus p2, we know that this is 0. So we have fp2 equal to c. Now, this is equivalent to, I prefer you to write c equal to fp2. Why? Because this is unknown. And this one is known. Okay, so fp2 is a value, then you know. So now you get your c. So how you gonna do it? You need to solve a simultaneous you need to solve a simultaneous continuous question. Okay, simultaneous equation. So what you need to do, you know what is your c value, substitute into here. Okay, you already have your c. Next, you need to find your a and your b. Then by solving this equation. All right. Okay, now let me show you the notes. Okay, I'm not going to teach you how we're gonna solve the equation in the class. Okay, so you have 3 equations. You already found your c. Okay, so what you're gonna do? Okay, you need to solve the 3 equations first. You have your c. This is known. Next, you do substitution. Blah blah blah. You will get your b and your a here. Okay, so this is your C, this is your B, and this is your A. Okay, I think I attach my calculation. So you see the 35A, B. I'm not sure, do we have a C? Let me check. Okay, at 35A and B is I show you the step, how we're gonna get the A, B, and C. okay, the unknowns, all right? So I will leave this for you to look it at home, okay? This is just solving an equation. It's just like for you to find the unknowns, all right? So solving a simultaneous equation, then you will be able to get your A, B, okay? C is already have it, okay? It's directly, okay? So go back home and look at this, okay? Now, these three formula, A, B, and C, you need to know, okay? Now, I know that A and B is really challenging for you to memorize, okay? What I'm gonna suggest to you will be, if Mueller methods pop up in your exam, okay, you just need to remember these three and spend a bit of time to solve the equation and get what is your A and B and C. Do you get what I mean? Okay, for those students, if you're not willing to do that, you want to memorize, then you go ahead. But I want to tell you, this is very hard for me. If you are very good in memorizing, then okay, you can go and memorize by yourself. But if you have the difficulty to memorize such a long thing, then you will derive. Okay, for me, I prefer to derive by myself rather than memorizing this A and B. It's so complicated for me. But if you are good at memorizing, then you go ahead. Okay, it's up to you. Okay, but you must know what is the A, B, and C represent. Okay. Okay, so what you're gonna do next will be, we want to find what is the answer for P3, okay? So you have the information of P0, P1, and P2, but you do not have P3. So in order for you to find the P3, you need the information from P0, P1, and P2, okay? So what you're gonna do here, you do not need to know further exact, because we have this quadratic formula, okay? So they are actually using, because you are using a quadratic curve, okay? Quadratic polynomial to approximate the solution of a non-linear curve. So here they actually apply a little bit of the concept of the quadratic formula, because quadratic formula you're kind of familiar with, right? So it is like b plus minus times the square root of b squared minus 4ac over 2c, but this is kind of the upside down, okay? So you do not need to know how we get this formula, but if you're interested, I encourage you to figure it out how we get this formula by yourself, okay, by you yourself. But for this course, we are not going to ask you how you are going to derive this formula. You just use it, okay? So I need to draw your attention. You need to memorize this formula, okay? And there are another things that you need to be careful, because square root of b squared minus 4ac. Now, if your b squared minus 4ac is a negative number, so we know that when you take a square root of negative number, it is a complex number. You will not get a real number, okay? Now, you have to remember the approximate solution should be a real number, okay? So how we gonna deal with the b squared minus 4ac that is less than 0? Because if b squared minus 4ac is less than 0, so that means when you take the square root of b squared minus 4ac, this one will produce a complex number, okay? And we do not want a complex number as the approximate solution. Okay, so what we're gonna do will be, first, okay, I just want to summarize. Okay, what you're gonna do is you have to remember this formula. Okay, this is the final formula that you need to remember. So I put a star. Now, how to define the sign for the square root? You want to choose positive or you want to choose negative, okay? To cater the problem of the complex root, okay? Complex root that we're referring is this one, okay? So what we're gonna do is we have to choose this one. The sign of this must be agree with the sign of B, okay? So that's why I summarize it in this form. I put sign B. So be careful. Let me highlight the sign B here. So what does it mean is, if your B is a positive number. Okay, so then your P3 will become P2 minus, okay, B plus square root of this. Okay, now if, okay, let me do this. If your B is a negative number, then we have our P3 is equal to P2 minus B minus square root of B squared minus 4AC. This is 2C. Okay, let me scroll down a bit. Okay, so remember, if B is positive number, this is the formula that you're gonna use. If your B is negative number, this is the formula that you're gonna use. Okay? So stopping criteria is the same. It will be given in the question. They will tell you when you have to stop. Okay, so you just need to know which formula that you need to use for the Mueller's method, because it is depend on the B, whether your B is positive or your B is negative. Okay, so if your B is positive, you need to use this formula. If your B is negative, you need to use this formula. Okay, so now let us take a look for the example 8. Okay. Okay, you see, you want to find a root, okay, for the polynomial this fx using numerical technique. But here I want it to be specific, that is using Mueller's method. Okay, so you have 3 initial conditions. So you see, in the exam, sometimes they just say using numerical method. Then you see, they give you 3 info, 3 initial point. This is a time we test whether the student know which method to use or not. Okay, be careful. Sometime in the exam, we will say, okay, we want to find the root for the function fx using Mueller's method. Okay, you are given x0, blah, 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 x1 equal to blah, 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 and x2 equal to blah, blah, blah. Okay? Sometimes we do not tell you which method you have to use. For example, find the root of the polynomial fx given that x0 equal to blah, 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 x1 equal to blah, 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 and x2 equal to blah, blah, blah. Okay? So in this case, if student use Newton's method, secant method, or bisection method, then you basically only use 2 info. Okay, bisection method is totally out because you are not given an interval. So either Newton's or secant. Some of the students may choose Newton, some of the secant may choose secant. Now, if you choose Newton and secant, you only use 2 information. So you will have a leftover info. So usually you choose this one and this one, but not x2. So this one, you do not use it. Then problems will come, okay? Because when you find the x2 may not be exactly equal to negative 0.2, okay? So you see, so in this case, we want to test a student. Do you understand? If you are given 3 initial points, which method you have to use? If you use Newton and secant, you may not be correct because you have a leftover information that you have been used, that you do not use. Now, always remember, whatever information they given in the question, you have to use it. Okay? Now, you see, they tell you 2 condition stopping criteria, either this one, okay, not either. We use 2 conditions to check when you have to stop. One is this absolute of xn plus 3 less than 0.001, and your absolute value of xn plus 3 minus xn plus 2 less than 0.0001. Okay, so these 2 stopping criteria, you have to use it. Okay, so what you're gonna do right now will be, first, you know that you have to use Mueller's method. Okay, let me stop this. I would like to use a paper. Okay, let me share this. Okay, so actually I would like to do the example 8 here. Okay, so I'm looking at example 8. So I write down you are given fx equal to x power 7 plus 3x power 6 plus 7x power 5 plus x power 4 and then plus 5x cubed plus, 2x squared and then plus 5x and then plus 5. Okay? Now for exercise, example and exercise, I try to use those complicated function. Okay, but in the exam, you will not have such a complicated function. Your function should be simpler a bit. Okay? Now, this is the first information. Second, you have x0 equal to 0. And then you have your x1 equal to negative 0.1. And you have your x2 equal to negative 0.2. Okay? Next, you have a stopping criteria. Okay, so one is absolute of fxn plus 3 should be less than 0.0001. And another stopping criteria is the absolute of xn plus 3 minus xn plus 2. It should be less than 0.001. Okay? So now what you need to find? So you need to find the root. I'm not sure how many roots you have of fx. Okay, usually we look for one root. Okay, so I put one root. Okay, so find the root of fx. So this is your target. Okay, now formula. Okay, so you can write solution. Okay, so let me write down the solution. So first of all, which method you need to use? So we know that we are going to use the Mueller. Okay, now what is the formula? Okay, so for the Mueller's formula, we know that we have first is xn plus 3 equal to xn plus 2. This is P3. This is P2. Okay? So minus B plus what is the sign of your B? If your B is positive, so here you take positive. If your B is negative, so you take minus. Okay? Times the square root of B squared minus 4AC. So this is 2C. Okay, so next you want to tell me what is your ABC. Okay, the A formula, that's pretty long, but I can convert it. So I write down here. So we have xn plus 1 minus xn plus 2, okay, times fxn minus fxn plus 2, okay, minus xn minus xn plus 2. Oh, guys, I do not have enough space. Do you mind that I write the next one here? Okay, multiply by, okay, this one multiply by here, okay? F xn plus 1 minus f xn plus 2. Okay, and next we divided by xn minus xn plus 2 times with xn plus 1 minus xn plus 2. And next we multiply by xn minus xn plus 1. Okay, so this is your A. Okay. Next, I will go for B. Okay, so your B is equal to B also is a very long one. So we have xn minus xn plus 2 square times fxn plus 1 minus fxn plus 2. And then minus, okay, continue, all right, continue. So I write at the next line, minus xn, I'm sorry guys, because I do not have enough space and it is very difficult for me to write small size. I'm afraid that some of you may not see clearly, okay? Minus xn plus 2 square times with fxn minus fxn plus 2, okay? And next we divide it by xn minus xn plus 2 and multiply by xn plus 1 minus xn plus 2 and then times with xn minus xn plus 1. Okay, if you notice, this one, I just highlight this one and this one, they are the same denominator. A and B has a similar denominator. Okay, A and B has a similar denominator. All right, only the nominator is different. All right, so, and we have the C, which is equal to fxn plus 2. So C is really easy. Okay, so these are the formula involved for Mueller's method. Okay, so what you're gonna do is next, you need to create a table. Okay, you're gonna have a very big table. Okay, so, okay, let me write down here, put your answer in a table form. Okay, guys, please forgive me, I may write quite small. Okay, first you need to have an n. Okay, next you need to have a fxn. Hey guys, do you mind that because I don't think I have enough space, okay? I will put column 1. What is a column 1, column 2, column 3 all about? Okay, I think this is better. So because you can write your solution in a landscape page, okay? You write it in a landscape, but here I have a portrait, okay? So first column, okay, so column 1, okay? This is n, okay? Column 2, we have xn. Column 3, we have fxn, okay? And column 4, we have xn plus 1. Column 5, you see, you have n, xn, fxn. So column 4, xn plus 1. So of course we expect column 5 is fxn plus 1. Okay, next, because we have a xn plus 2, right? So then you repeat column 6, this is xn plus 2. Next, column 7, that will be the f value, xn plus 2. Okay, next, we have a column 8. Okay, now we know that column 7 is equal to fxn plus 2, and this is also equal to the C value. Because if you see from here, your C is this one. Okay, so that means your column 7, the value of fxn plus 2 is equal to C. Okay, so you can write this is C equal to fxn plus 2. So this is your column 7. Okay, so I write it here. Okay, so next, column 8, you need to find what is your, so column, I put arrow is better so that you know what's happening. Column 8 is you need to calculate your B. How to calculate your B? This is a bit complicated calculation. You have to use this formula, the B formula, okay? So after you calculate B, you need to calculate A using this formula, okay? So column A is B, and next column 9, that will be your A, okay? So after that, you can begin to calculate what is your xn plus 3. So this is using the Mueller's formula, using this formula, okay? So this is a formula for you to calculate your xn plus 3, okay? The sign of the B is very important, okay? So this is the sign. You need to know the sign of B, okay? Now, let us proceed with column 11. That is a stopping criteria. Okay, column 11, you need to check what is the absolute fxn plus 3 value. Okay, is it a positive or is it a negative? Now, I would suggest, because in order for you need to find back when you increase your n, you need the information of your fxn plus 3, right? So I would suggest, okay, this is an option, all right? Column 11, some of the students will directly put the absolute, okay? And then you proceed with column 12, that is to find, you have two stopping criteria, right? So you have to make sure both of the stopping criteria are satisfied. Okay, next you are done. Okay, another option, okay, or this is better, okay, if you wish, okay. Column 11, you find f xn plus 3. You just add one more column if you have a space, all right? Then column 12, then you find what is the absolute value. Okay, and column 13, you find another stopping criteria. That is this one, xn plus 3 minus xn plus 2, the absolute value. So I give you the option, okay? The difference will be this one and this one. So you choose which one you like, okay? Now, for the example 18, okay, it is too long. So what I'm gonna do is I would like to give you what is the answer, okay? So the answer for the example A, okay, is the root, okay? The root is your x star is equal to negative 0.706826. So this is the answer. Now, for what my solution is, I need to do the n, start from 0. Okay, so the n that I need to calculate will be, I start from n equal to 0, 1, 2, up to the last one, 5. Then I will be able to get this answer. Okay, so I will leave this for you to try as an exercise at home. Is it okay, guys? So you just jot down the answer for the example 8 and the number of n that you need to compute, okay, in order to help you to find the solution for the example 8. Okay, so let me see what else that we are going to discuss. Okay, now let me share you this. Okay, so if you see this example 9, okay, you have seen this example actually. Do you remember this function? So this is a function that we have seen from the bisection method. Okay, so bisection method, we have used this similar function to find the root. Okay, so here I would like to give you the answer for this example 9, okay? And you compare what is the difference between if you use bisection method, Seeker method, Newton's method, and now Mueller's method. So are they having the same answer, or what are the difference between the answer? Okay, so I give you the answer. Okay, let me write down the answer that I have obtained. Okay, first of all, I do n started from 0, 1, 2, 3. So this is the n that you need to compute. And I get the root of the function fx is 0.420683. Okay, if I'm not mistaken, it's the same answer from the secant method, Newton's method. Okay, but I would like you to try it just in case I do the wrong computation. Okay, so I would like you to do these as an exercise at home. Okay, practice. Okay, practice makes perfect. All right. Okay, guys. I'm done for this chapter 2. Now, I would like to ask you, do you have any question that you would like to ask? Any question? No question? Okay, so if no question, then next week I'll begin with chapter 3. Okay, I just want to run a check. Is Nurul, Karunisa, and Akila, are you guys here with me today? Nurul, Karunisa, and Akila, are you guys with me? S66067 and S68439, the matrix number. I can't see both of them with me today, right? Okay, so I assume that they are not with me today. Okay, that's all from me today. If you know these two students, please ask them to text me, okay? I just want to make sure that are they in my group or Dr. Azwani group? I got confused, okay? Okay, guys, if you have no other question, then I would like to end our class today, and I will see you next